Hi everyone, I'm very glad to present our new LDBC SNB audit test results with Galaxybase, a high-performance distributed graph database. I'm Chen Zhang from CreateLink technology. Firstly, I would like to introduce our company. Our company was founded in 2016 in Hangzhou, China. In 2018, Baidu Venture invested in us as our angel round. 2019, our product is ready to market, and we participated in a number of national standard associations. In 2020, we formed alliance with Tencent Cloud and Hillhouse Capital invested in us. 2021, Tencent and other VCs invested 2 rounds in us for over $20 million. Our core product, Galaxybase, is a native distributed parallel graph database platform. We are the current LDBC SNB world record holder and also the current largest scale graph record holder, up to 5 trillion edges. Our customers include Tencent and 2 of the 5 major banks in China, Power Grid, etc. We have a number of patents, including a US patent on distributed graph database platform, system, and methods. We also got a number of industrial recognitions, including Amazon AI Fusion Award and Excellent Solution Award for IT services of commercial banks, etc. Generally, graph technology offers a way to exponentially grow the value of data because we connect the dots and each piece of information carries a network effect, amplifying the total value of connected truth. The development of graph application also evolves through time from small-scale knowledge graphs to larger transaction graphs, and then further to events and behavior graphs towards trillion scales and beyond. Here is the LDBC SNB record I will soon talk about more in detail. LDBC SNB is a world-recognized most complete benchmark of graph databases so far. We broke the previous record and achieved 70% higher throughput, up to 72 times faster in response time. The full disclosure report can be found on LDBC Council's official website. Another world record we broke is the largest scale graph. Neo4j announced 1.2 trillion graph in 2021 using over 1,000 AWS machines. We, together with Chen University Supercomputing Center in China, achieved 5 trillion edge graph processing with 50 supercomputing machines. The 2 major reasons we can achieve such performances are, firstly, we designed and implemented our native storage such that we can control in fine grain which data store at which location distributedly. Secondly, we redesigned and implemented a number of graph algorithms specifically designed to exploit the distributed machines in parallel, based on bulk synchronized processing model and message passing to coordinate parallel computation across distributed machines where data locates. Data locality is exploited to full extent with optimized message passing in transit. Now let's talk more about the LDBC SNB audit test record. Firstly, why LDBC? We used public datasets to test and compare graph database performance earlier, but due to the lack of a unified test standard and a single testing content, we could not measure the performance in the actual production environment. Therefore, we aim to choose an authoritative, well-standardized, and realistic benchmark to evaluate our system. We found a great fit with LDBC, a non-profit organization with a set of scientifically objective benchmarking standards that aim to define standard graph benchmarks to foster community around the technology of graph processing. With members from industry and academia, including organizations and individuals, LDBC is the most credible graph benchmarking committee in this industry. We participated in the LDBC SNB benchmark, and this benchmark measures database performance by simulating real query scenarios under officially generated social datasets of different sizes and examines the ability of graph database to perform iterative queries and insert updates under concurrent situations. On the 16th of last month, an exciting day for us, we completed the LDBC SNB audit, and our record broke the record with absolute performance advantage, becoming the current holder of the best record on LDBC SNB. This is the complete process of the audit test. The blue shows the tools provided by task force. The pink indicates the work that the auditor needs to do for the audit, and the yellow represents what the test sponsor like us need to prepare. The auditor will provide data generator and test driver tools, which include the functions of the data generation, sample generation, correctness verification, and performance testing, making it a very complete set of benchmark testing process. We need to provide a graph database with high performance that meets the requirements of satisfying correctness, transaction, and recoverability. B, the use a usage process description document. C, the implementation of LDBC SNB correspondence case. D, the implementation of the test driver. And E, the configuration that needs to be audited. We give what we prepared to LDBC auditors, and all the benchmarking operations are performed by the auditor. The audit covers 4 areas: performance correctness validation, asset validation, and recoverability validation. For graph database benchmarking, the first thing we need to ensure is the correctness of the result. Otherwise, the test performance is meaningless, even if it's excellent. LDBC provides a correctness testing mechanism by screening out third-party graph databases for testing and comparing the correct results obtained with well-tested graph database. This time, the graph database Neo4j version 4.4.1 was chosen to be the standard for the correctness validation. The test results of the Galaxybase were compared with the results of Neo4j and passed the correctness validation. Transaction validation is an important step in achieving a fair comparison between systems in graph database benchmarking. LDBC transaction isolation requires a read-committed level. Galaxybase acid test has reached a serializable isolation level, which is stricter than the read-committed isolation level required by the SNB interactive specification. The purpose of the recoverability validation test is to ensure that the data in the repository is not lost in the case of a database failure. In real scenarios, there may be power failures, fires, and other unexpected conditions where recoverability is a very necessary capacity for the database. The official LDBC recoverability validation is to directly turn off the device when the benchmark test execution reaches 120 minutes, and then to reboot the system, and the data of the last successfully inserted record in the LDBC log should remain intact and durable in the graph databases. And Galaxybase also passed this recoverability validation. The benchmark performance test is conducted in 2 phases. The system under test must undergo a warm-up time of at least 30 minutes, during which the performance of the operation is not considered. The purpose of this is to put the system in a steady state. Next, the system under test is benchmarked during a 2-hour measurement window, and the operating time is recorded and checked to ensure that the 95% on-time requirement is met. Let's explain a few key configuration parameters. Thread count, the number of concurrent benchmark tests, which means, and time compression ratio, for example, when the compression ratio is 1, assuming that the same test item sends the request interval of 100 milliseconds. If the compression ratio is changed to 0.5, then the request interval becomes 50 milliseconds. Therefore, the smaller the compression ratio is, the more frequently the requests are sent, the higher the throughput is, and the higher the performance requirement of the graph database. Operation count is the number of tests, and this number needs to meet the requirements of 2 hours of formal execution. The performance results are divided into summary results for all test items and results for individual test items. Before Galaxybase, the record was held by 2Graph in 2020. 2Graph used to test on Amazon servers. This is the system environment configuration they used. The tests were conducted on datasets SF30, SF100, and SF300 in this configuration, and the throughput was around 5,000. As you can see in this table, this time, Galaxybase chose the same system environment configuration as 2Graph. Under the same configuration, Galaxybase throughput improves on the previous record in all cases. You can see the data in column 4. The throughput improvement rate for each of the 3 datasets is about 70% over the previous record. In addition to the throughput, the LDBC test statistics are very detailed. Here is the result for SF100, for example, the response times of the previous record and the response time of the Galaxybase, respectively. The boost multiplier is also listed here. As you can see from the table, Galaxybase exceeds the previous record for all individual response times. Galaxybase shows better performance in both different query data volumes and query complexity, and this advantage increases with the size of the dataset, fully demonstrating that the Galaxybase excellent support for large-scale data processing. Here, we summarize the average and maximum performance response time improvement for each dataset. Our overall average performance improvements over 6 times, and our maximum performance improvements over 72 times. Here's a detailed list of test items. As we can see, the tests are very extensive and covers a wide range of graph patterns and choke points applicable to not only social network scenarios, but also very general graph processing requirements regardless of specific use cases. Therefore, LDBC SNB is very well organized and used in many other use cases such as banking, energy, etc. Galaxybase performance in this LDBC SNB audit stands out to break the world record. The key lies first in the storage, and the way of the storage affects the performance of the graph database read and write. In terms of storage design, Galaxybase uses a proprietary native graph data storage structure. The special optimization for index-free adjacency of graph data enables point edge queries to be done in an extremely efficient way. The core storage engine does not rely on any third-party open-source components, ensuring autonomy and control while allowing graph query and graph computation to be better optimized with the underlying storage layer. At the query execution layer, Galaxybase compiles memory data more compactly through its memory allocation and management mechanism, at the same time greatly reducing JVM GC time by using off-heap memory. In terms of parallel control, Galaxybase provides a parallel iterative graph traversal approach, uses multi-version control to reduce lock competition, and can adaptively allocate the number of threads for parallel iterations based on the number of neighbors during neighbor iteration to achieve the best use of the system resources. Besides the storage advantage, what is closely related to the performance is the implementation logic for each LDBC SNB case, and this is also the algorithm advantage of Galaxybase for complex deep chain queries. Galaxybase can adaptively adjust the query link path to get the desired results in an optimal way with the least amount of resources. For high throughput, low latency query requirements, in addition to storage and algorithms, the development approach also affects performance. If the case logic is implemented on the client side, um, the execution process will certainly generate a lot of communication burden with the server side. If it is implemented directly on the server side, in the face of real-time changes to the logic tuning operations, a way to reduce the cost of server-side operations can be updated online when needed. Therefore, Galaxybase has designed a native PAR API interface, parameterized algorithm routine. It allows users to run custom procedurals and functions on the server side through Java code implementation to gain better control over the query execution process and pursue the ultimate performance. In practice, users can choose the most suitable solution according to different scenarios and needs, weighing various factors such as the ease of use, development manpower, system resources, and performance requirements. Galaxybase also offers easy-to-use graphical user interfaces for users to directly run algorithms to solve problems and make real-time decisions. Because of the performance advantage and ease of use, Galaxybase has a number of key customers. For example, in IoT, we built an IoT network based on device, Wi-Fi hotspot, and ID information for analysis of co-appearance and other cases in support of its banking, government, and public security customers with 300 terabytes of original data, 5.4 billion vertices, 3.75 trillion addresses, and 18.77 trillion properties. In one banking scenario, we built a user network of related entities, contacts, phones, addresses, company, IP, email, etc., with various types of relationships, guarantors, transactions, family members, work addresses for various fraud detection cases. Here's a list of some of the partners and customers we have. Please feel free to contact us for further information. Thank you.